There's one more way to combine statements I'd like to discuss, and this is called the biconditional statement. You will either see this type of arrow or with two bars. This is red, P, if and only if, Q. And in a way, I can say quite simply, when this is true provided P, let's see, this is true provided P and Q have the same truth value. If we think about a truth table for P, if and only if Q, well, we have these four possibilities for the two input variables. And P, if and only if Q is true only here and here. It means either both P and Q are true or both P and Q are false. They have the same truth value. Now, there's another way to think about this expression that we will actually use when we get into proving if and only if statements. But before I write that down, I need to define logical equivalence. Okay, and this is general definition to compound statements are logically equivalent provided, well, they have the same truth value for every possible input. Now, we will justify or really prove that two statements are logically equivalent or not logically equivalent for that matter. And how do we do it? Well, if we think about a truth table, every possible input is listed in a truth table. And so, two statements will be logically equivalent provided when we list all the inputs, the columns for the two statements have the exact same pattern of T's and F's. Okay, so to see logical equivalence, we will, as I mentioned, use truth tables. And this one, the if and only if, which I've defined to be it's true precisely when P and Q have the same truth value, we can see what it's logically equivalent to using a truth table. We will see, so let's show, and this is our first verification of a logical equivalence, that this P, if and only if Q, is logically equivalent to, well, it's P implies Q and Q implies P, okay? So this over here, the right-hand side of this equation, that is the side we will work with when we prove if and only if statements a little bit later in the semester. But let's show this, okay? Well, what I can do, you see I already have a column for P if and only if Q, and then I can just make enough intermediate columns to be able to get myself to this right-hand side. We see the pieces. We need a column for P implies Q. We need a column for Q implies P. And then we AND these two columns. So we will get to this final P implies Q and Q implies P. And the way you want to do a truth table is have really just sort of one step per column. Okay, so you see this column we're interested in the end, in this last column we should see T, F, F, T. Then we would know this and this are logically equivalent, which is our goal. Okay, well, P implies Q. The only time this is false is when we see a T followed by an F. So this is false here, and it's true everywhere else. Now we're going the other way. We look at column Q, and then it implies this one. So the only time this is false is when we have this T followed by an F. This happens in row 3. This is false. Everywhere else, this is true. Okay, now we are anding. So we look here, and we perform the and operation. Okay, true, true, the and is true. False, true, the and is false. True, false, the and is false. And true, true, the and is true. Now, okay, I'm going to finish the proof of logical equivalence below. So it's a truth table plus a sentence. So as columns 1, 2, 3 and 6 have the same truth values, well, this holds. P if and only if Q is logically equivalent to P implies Q and Q implies P. And this is how a proof of logical equivalence goes. Well, let's do another example. Let's prove if you take P or Q and then a not, so not P or Q, this is equal, and this means logical equivalence here to not P and not Q. This, I will just say, is one of De Morgan's laws. The other one, just as a comment, the other one says if you take not P and Q, this is logically equivalent to not P or not Q. This is just a comment, but both of them talk about how do you negate an or. Similarly, how do you negate an and? What it says, you switch. The or goes to an and, the and goes to an or, but then you negate each piece, okay? But let's show this one. We'll show this one, and I will say if you want to show this one with a truth table, it would be a very nice exercise. So let's prove the one in black. We have 2 input variables, and then I need some pieces. So I need the or, and then I need not P or Q, okay? And then I need not P, not Q, and then I am taking an and, not P and not Q, okay? So this will have everything we need in the truth table. And then again, I have these 4 possible inputs. You could write these in a different order. It would be fine. But you do need to have all 4 possibilities. P and Q can each be both true and false. So there's 4 possibilities here. Now, we are or-ing, which means this is the only time the or is false. And then we look at this column and we perform not. So it switches all of the values of truth. The trues become false, the false becomes true. Okay. Now we have these 2 columns which are nots. First is not P, and then is not Q. Okay. Finally, I take an and. The only time the and is true is when both are true. So I'm taking this column, performing an and. So I only have true here, and everywhere else is false. And which columns are we trying to show here for this logical equivalence? Well, this one and this one. So now we will complete this proof of logical equivalence. This is column 4, 7, as columns 4 and 7 have the same truth values for all possible inputs. Let's see, we have shown logical equivalence. We have shown this one of De Morgan's laws. So P or Q is logically equivalent to not P and not Q, okay? This is logical equivalence, which we prove using a truth table plus a sentence. Here's one more of this type. We want to prove P implies Q and not P implies Q is logically equivalent to the statement Q. Again, we have two inputs, P and Q, so we will have 4 rows of our truth table. And then we have to think about the intermediate steps that we need. Well, I need a P implies Q. I need not P. I need not P implies Q. And then the final step here is it's an and. So I need P implies Q and not P implies Q. And we should see that this very last column and the column for Q are the same pattern of T's and F's. So I begin with my 4 possibilities for the input variables, and then we have an implication. As I mentioned, it's only false one time, is when P is true and Q is false. Every other time, the implication is true. Now I'm taking not P. Now, not P implies Q. So I look at this column here. And then I look at this column. This column implies this column. Again, I'm looking where I have a false. It will be in this column where I see a T, but over here I see an F. And you see this is the bottom row. So this is false here, and it's true everywhere else. The final step is we take column 3, column 5, and we take an and. So it's true here, false. We have 2 trues, so this will be true, and TF, we will have a false. Here we go. Column 2, this is Q. Column 6, this is this expression. You see, both go TF, TF. So we are finished. We just have to make that remark. As columns 2 and 6 have the same truth values for all possible inputs, well, this proves that P implies Q and not P implies Q is logically equivalent to Q. And this is what we were trying to show. There are a few special types of statements. So a tautology is a statement that is always true. And sometimes you will see this written as this sort of bolded T for tautology, and a contradiction is a statement that's always false. And you will see this as a sort of bolded F. Now let's see an example of a tautology and a contradiction. Well, let's take P and not P. Similarly, let's take P or not P. And one of these will be a contradiction, one of these will be a tautology. And how can we figure this out? Well, truth table, of course. So let's take P, not P, and then we have P and, not P. We have P or, not P, okay. Well, this only has one input variable, so we only have 2 rows in our truth table. It's T and F, and we switch the truth value for not P. Now, we have an and. Look, the and is false and false. Now we have an or. Look, the or is true and true. So this truth table justifies this one. This is logically equivalent to this here. And this one, the or, this is here. Okay. This one is a contradiction, always false. This one is a tautology, always true. But you can have expressions involving more than one input variable that are tautologies or contradictions. Okay, it just means the statement is always true, or it means if it's a contradiction, the statement is always false. Now, given an implication, P implies Q, we have sort of 3 related statements that we can make. One is the converse, one is the inverse, and one is the contrapositive. And what are these 3? Well, the converse is Q implies P. The inverse is not P implies not Q. Maybe I'll put parentheses on all of these. And finally, the contrapositive is not Q implies not P. Okay, so how are these related to each other? Here are all the columns that we will need to fill in a truth table that has the implication, the converse, the inverse, and the contrapositive. And we begin with these 4 possible inputs. Okay, the first thing we do, we negate P. Here is not P, and similarly for not Q. Now it's an implication. P implies Q, which is false here. Then Q implies P. This is false here. Okay, what about the inverse? Not P implies not Q. We're looking here to here, an implication. So here's the only T followed by an F. It's in row 3. So we have an F here, T's everywhere else. Finally, we are going not Q to not P and an implication. So we have a T followed by an F, and this is the only one. It's in row 2, false, and it's true everywhere else. So now just stare at what we have, and we can see some things, wonderful things. Well, look, this column and this column, they both go TF, TT. This says that the implication and the contrapositive, they are logically equivalent. And similarly, look at these 2, TT, FT. This column and this column, maybe I'll write this up here. These 2 are logically equivalent. And these 2 are logically equivalent. But also, I would just abbreviate here, logically equivalent. I could have just written also an equal sign because that's what equals means when we were talking about statements. And so you see, one neat thing we get from this is we will later be proving. That's the whole goal of this course, right? To write proofs, communicate mathematically, think logically, like this. We will be proving P implies Q type statements, the implication. But sometimes, if you want to prove this sort of directly, it presents a challenge, and we will want to have other ways to go about it. And one way is by working here, because the contrapositive is logically equivalent to the implication. This will be one of our proof techniques. Well, it's called proof by contrapositive, and this is coming. We will end today with proving this logical equivalence. First of all, we notice we have 3 input variables, so it's a nice exercise to even think about how many rows we will have in our truth table. But also, this identity is one listed in your text together with many others that you can, any of them, you can justify using a truth table. And for instance, 2 of them are the De Morgan's laws, which we did one of those today as well. So, well, we have PQR, and then I need to write some intermediate steps for the columns. Let's see, I need I need Q and R. I need P or Q and R. So this is my left-hand side. Okay, then I need P or Q. I need P or R. And then the final column, I take this, and I and P or Q and P or R, like this, okay? So this will be the right-hand side, and I should get the same pattern of T's and F's, and then I will have justified the logical equivalence. Now, we have, you see, 3 input variables. Each one can be true or false. Well, we will have 2 to the 3, which is 8 possibilities for inputs here. So, half of them here will be true, and half of them will be false. And then I can put them in pairs of 2 here. And then I can alternate by 1s here. Oh, yeah, false. And if you notice, we have 8 listed and none of them are the same. Okay. Well, here we go. Q and R is true only when both Q and R are true, which is here, and it's false every other time. Okay, now we take P, or this column. Now I'm ORing. So if I have a true in either one or in both, it's true. Okay, so true, 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 and then I have, we have 3 falses, false, false, and false. You see? False, false, false. The OR is false. Okay, great. So this here, we should see 5 trues followed by 3 falses in the very last column. Well, we have P or Q. So this is false only when they're both false, which we see is the bottom 2 rows. False, false, and then we have now we have P or R. And again, this one will be only false when both P and R are false. So I'm just scanning for that time. This is the here, third to bottom and the bottom. So it will be here and here, and then it's true everywhere else. Now I'm on the very last column. Okay, I take this, and I and so the only time it's true is when I have T and T. And you notice, just looking at it, that's the top 5, and then false, false, false for the and. Now, look how great. This is column 5, column 8. We see the exact same pattern. So as columns 5 and 8 have the same truth values, we get that this P or Q and R is logically equivalent to P or Q and P or R. And this is the end. We did this truth table. We had 8 rows, right? And thank you.